All right. Tom Vallone, I hardly know where to start with him in terms of introducing him. He's been around this field for a long time. He used to do a lot of different things, and he still does do a lot of different things. And it's really great to have him around because he's one of our greatest coordinators and correlators of information. He's president of Integrity Research Institute. He also edits the journal Future Energy and E-News. So he makes a great contribution now. In the past, he's invented several instruments. As a matter of fact, my first magnetic field meter that I used in my consulting practice I bought from him, and it was a very good meter. Really got a lot out of that for several years. And he's also invented a dental vapor ionizer and a static field Gauss meter, ELF spectrum analyzers, and several other things. He's taught at the State University of New York, Erie Community College, and he's also taught a number of other courses all over the place. But with his varied background, he's become one of our best speakers and one of the greatest experts on advanced technology in the world today. Tom Vallone.
Thank you very much. It's a pleasure to be here and to address you today about a very important topic. I'm hoping this is not too loud and I'm getting feedback. Everyone can hear me okay? Good, good. I can tell by your silence that you're awake and alive and paying attention. Today we have a confluence of a lot of different encouraging signs that what I'm about to present to you has great significance. As Michael pointed out, some of us have been pursuing the field of alternative and emerging energy sciences for decades. I literally started in 1980 pursuing the Gravitational Field Conference in Germany. And from there, it became a habit. Every year, I'd look for something to give a talk at and learn more and correspond and write and so forth. So essentially, after 24 years at this, you kind of wonder if the word free energy is ever going to become acceptable or basically still shunned by the mainstream scientists and, of course, the government. But as I pointed out, we just today, this week, as a matter of fact, received some encouraging signs. And I will cite other ones in my presentation as well. But this one's hot off the press. Los Angeles Times, July 25th, 2004. The title of the article is Mining the Imagination for New Energy. Scientists call for a research blitz targeting extreme possibilities. Now, doesn't that sound like a fringe article from Extraordinary Technology? No, it's in the LA Times. And just to paraphrase to quote one of the leading paragraph sentences, which criticizes both the presidential candidates, for just looking at standard alternatives. They're writing in the journal Science, and Caldera and 17 other eminent American and Canadian scientists conclude that the only hope for solving the world's looming energy shortage is to consider things we've barely imagined. Hello, people are waking up. This is wonderful. They propose a research blitz of previously unimagined proportions, far beyond what any politician is currently suggesting, in search of entirely new carbon-free technologies. I think we should give them a hand if they were here, But see what desperation does? They start to look for things that perhaps might last more than 100 years. And of course, as we know, the oil industry is just about a 100-year lifespan. That's all we can expect, if at all. So let me give you another warm-up to the topic at hand. And to reference this, we've also had a presentation. I personally have given one called Understanding Zero-Point Energy that's been actually reproduced as an article in many places, Infinite Energy Magazine, Explorer, and so forth. And that was in 1999, so that video is also available to introduce zero-point energy. Now, what is zero-point energy? I'm going to show you many different definitions, but let me quote Nikola Tesla. Many of us in this crowd know who Nikola Tesla was, celebrate his greatness. Well, in 1891, the world's greatest electrical futurist, Nikola Tesla, stated, quote, "Throughout space there is energy. Is this energy static or kinetic? If static, our hopes are in vain. If kinetic, and we know for certain it is, then it is a mere question of time when men will succeed in attaching their machinery to the very wheelwork of nature. Many generations may pass, but in time our machinery will be driven by a power obtainable at any point in the universe." And so there, ladies and gentlemen, is the basic birth of the concept of zero-point energy. Tesla was so intuitive that he basically perceived the existence of something that was just barely being discovered in the fringes of scientific literature. So let's begin our slides and start to discuss more in detail the actual definitions and information that will give you a basic understanding and also, I hope, an excitement for this field. For years, I felt zero-point energy was something unimaginable, beyond comprehension, and the numbers were too large to really appreciate. Well, as a matter of fact, NASA has helped us in this case because they're pointing out on this website that zero-point energy essentially has random electromagnetic waves, and this is the first very important part to it, that if you realize vacuum fluctuations are real, you've come away from this lecture with a whole new understanding of reality. Vacuum fluctuations are real. For years they were called virtual, and they still are in the textbooks. They're only virtual particles, therefore they have no effects. And that's what mainstream science always thought. But the enormous energy density, which is still a number that's been bantered around like crazy, depending on who you listen to, it's 10 to the umpteenth joules per cubic meter. And as I say, the exponent is debatable. It's always less than 100, but it's more than 10 to the 10th. And of course, the fascinating part, which Harold Puthoff has contributed to, is that gravity and inertia have now been fairly theoretically proven to be related directly to zero-point energy, the actual field effects of zero-point. When you go around a curve, you're actually bumping into zero-point particles, and that's why you feel the inertial effects. And gravity is also the similar effect. And of course, the debatable part of it is whether or not there's an energy source available. Many people, like Robert Forward, went to his grave believing there was no energy source available. However, today we're seeing otherwise. And of course, the biggest evidence, which there's lots of literature in regards to this, is the Casimir effect. This diagram actually is one of the best, and in fact we have another one too. But notice the wavelengths here. We're basically showing, which this perhaps does not do justice to, the fact that as you place two parallel plates close together, and they can be other shapes besides parallel, you find that you start excluding some frequencies. And as you exclude some frequencies from that inner cavity, the outer cavity now has more and more pressure, literal physical pressure. And so the Casimir force is a real force that has sizable pounds per square centimeter pressure that's real. Now, the quantum vacuum, which is a good name for what we're surrounded by, even in our bodies, we're surrounded by what's called the quantum vacuum. What perhaps is the most important conclusion of the scientific community is that zero-point energy is not conserved. Hello, I just said something remarkably incredible. I said the conservation of energy law doesn't apply here. I mean, when I heard that, I said, my lights went off in my head. I felt this is an escape route. This is literally an escape route where, of course, the literature, and I'll quote lots of great scientific articles, where they basically say perpetual motion, oh, free energy, but no, of course not. Conservation of energy still applies. They can't admit that this statement is true, but it's already known to be true. So what we end up with is a new corollary of the conservation of energy that says, well, you got to include the zero-point field too. So if you get some energy from it, you may not have to return it, but at least acknowledge the source. And one of the best proofs, there's dozens of proofs of the effect of zero-point energy, is the one that basically can be seen in the laboratory now. As temperatures in the laboratory have become close enough to be fractional degrees, in other words, millionths of a degree from absolute, liquid helium stays liquid. It doesn't freeze. Every liquid, when it gets cold enough, freezes. But something's keeping helium liquid, and that is zero-point energy. There's nothing else available at that temperature to provide energy. And that's what we find. The exciting part about it is that when you remove the temperature dependence, all of a sudden that's the only thing left. And of course, this diagram is the one that I was referring to before, is that normally we see an experimental proof that the Casimir force pushes. It pushes the plates together, and with tremendous force, with an exponential third power and fourth power as the distances change. Now, to illustrate, there's actually a diagram here that's drawn below it. This is supposed to be a cloud chamber picture. And one thing we have to acknowledge is that electron-positron pairs are coming out of the vacuum all the time. And what you see in this particular diagram, too, which is not well reproduced in the slide, is a picture of your local electron. Every electron normally has been pictured as a single, perhaps, ball, a sphere. But as a matter of fact, this is an electron that is a sphere, but it's dressed. And the dressing is all the activity buzzing around this electron that is literally attracted to the electrical gradient. And the electrical gradient is something that I'm very excited about, because in any transduction mode you see throughout nature, whether it's gravity gradient, temperature gradient, or magnetic gradient, which I'm exploring now, the gradient itself is how fast it changes over distance. And at this distance, which can be femtometers, 10 to the minus 15 meters, you get a tremendous gradient. It's so big that one particular article, which I cite in my feasibility study, points out that if the gradient's high enough, you'll get decay of the vacuum. The decay of the physical vacuum is actually an article from Scientific American describing this phenomenon. So locally around every electron, every positron, every proton, a charged particle, the gradient's high enough to break down the vacuum. And when you break down the vacuum, it means, just like Paul Dirac said, you get all these negative energy particles coming to life. They literally have enough energy to pop out of the Dirac sea. And this picture, this image of the Dirac sea penetrating, permeating everything, but having negative energy, is the new quantum mechanical, quantum field theory image of what reality consists of. It's no longer the 18th century image of empty space. See, in the 1700s, they thought the vacuum consisted of emptiness. That's where the word came from, vacuos and so forth. Vacuo is a Latin word, and it means to empty things. But they found that when you take out all the gas, there still was stuff there. And you take out the temperature, bring it down to absolute zero, there's still energy there. So this is an important consideration. So think of the fact that there's lots of activity going on in the vacuum, and this has also been regarded as what's called the quantum foam. Now, there wasn't much activity in this area of research up until 1997. And in 97, what we see, January 21st, in the New York Times, is that Dr. Lamoureux from Los Alamos Labs performed what he called the most intellectually satisfying experiment with 5% accuracy that proved the existence of the Casimir force for conductive plates. And at the time, this was regarded as they say, a theoretical interest. But the possibility of the universal vacuum might actually be a false vacuum is now becoming an understandable reality. It's no longer a possibility. it's real. And Lamoureux's experiment woke up a lot of physicists who were on the fence wanting to stay in the classical mode, you know. And of course, I keep talking about how quantum mechanics has been like that for years, proposing a new reality to people who want to just think of cause and effect, billiard ball Newtonian physics. Well, it's a new reality out there. Now, the surprising thing is, and I'll refer to this a little bit later, we've found that the galaxies are accelerating away from each other. In other words, there's a repulsive Casimir force on a macroscopic scale. That's a tremendous new discovery. And the existence of this phenomena in the laboratory has also been verified. In this particular experiment, there's many of them, but Physical Review Letters, volume 89, 2002, really has, I would say, several very interesting ways to control the Casimir force. And so what we find, for example, is that the magnetic susceptibility is important. There's also the large range of parameters that are involved. And of course, even for experimental purposes, the permittivity and permeability effectively give you the control in terms of the impedance. So when you're dealing with an experimental environment, in other words, trying to build a black box that works, you might want to consider, as we have for centuries, the concept of push-pull. And so far we've only got a push, but now we've got a pull. We've got something pulling apart, repelling the same things that originally were attracting it. And it's all due to the impedance within that container. And what we find, and this is very exciting to me, is that there are a number of experiments, and I'm only going to cite a few, but the rest are in the feasibility study. And they're also, this whole study, by the way, is actually on our website. We have a hard copy available, but I've posted the whole thing for public release. It's in Word. You can download it. It's about 180 pages, about 3 megs of memory.
What's the website?
integrityresearchinstitute.org. And it's very technical. I make no bones about that. But what I do this is also my PhD thesis, is I had to follow a form which led me to do a literature study, a history of the phenomena. So you get built up from storytelling to technical information. So you can read along as much as you can, and then, of course, jump to the back of the book for the good stuff, the conclusions. And so that's what I'm giving you today are some of the very important conclusions. And this is also another very important conclusion here, is that as the temperature increases, the change of sign of the Casimir force changes. Now, why I emphasize these kind of controls is, as any engineer will know, once you know how to control the system, you can start imagining things that you can do to change one item and get a change in the other. If you want to force something to change and you know the temperature will do it, why not look at some temperature gradient as your input, and all of a sudden you get a Casimir force output. And that's exactly what scientists have done. And they've done it very creatively, as a matter of fact, as you'll see. Now, here's one scientist who, as I say, just passed away about a year ago, who basically was a pioneer in this subject. We looked for years for journal articles like this, and I believe this was 1994, no, 1984? Yeah, I believe 1984. Physical Review B. And the important thing is Robert L. Forward, for years, looked at the edges of science to see what emerging technologies were possible. And what he proposed initially was this could be a vacuum fluctuation battery. And to all of us who discovered this article, we felt, at least they're talking about it in the physical literature. In the phys rev literature, this is an important achievement to talk about zero-point energy there. Now, initially, he thought that this was perhaps a source of zero-point energy, but as it turns out, it basically is a battery storage facility. And what you find is that as you compare the forces on the plates, the Casimir force and also the Coulomb force, they tend to balance. And you can achieve a contraction of the spring when you pull charge out, and if you put in electrical current, then you stretch the spring a little bit. And of course, very little voltage is needed, as you see, to achieve the effect. So this really, I think, provoked, even if he was not very successful in designing something practical, it provoked a lot of thought. This one article basically, I think, caused a tremendous amount of thinking of Casimir plates, how to design them, what geometry would work, And the engineering approach, of course, is the most important. So the zero-point energy basics that we're looking at here really is the bottom line in terms of the important facts. And I would like to also add in this particular slide that the uncertainty principle, which you may have heard of as the basis of quantum mechanics, the uncertainty principle itself predicts zero-point energy. When you're looking at an uncertainty in momentum and position, and you're equating it to just the Planck's constant in the frequency over 2, that's essentially the zero-point energy quantum amount. It's basically half of a quantum. And we see the same figure here, 1/2 HF. In 1912, Planck discovered zero-point energy, and it was his second time around. The first time, his first radiation law just had this parameter. And what I always point out when I show this equation is if you do some creative math and you put in T equals 0 there, which is the absolute temperature, if you let it go to 0, then you basically get 1/0, which is infinity. E to infinity is still infinity, but then you've got HF over infinity, which is 0. So at temperature equals 0, this whole term drops out, and you're left with 1/2 HF. So this became the introduction to really thinking about and acknowledging the existence of zero-point energy. And Planck's constant, in case you don't know, haven't memorized the numbers, right down here, 6.6 times 10 to the minus 34 joule seconds. Now, joules, of course, is a unit of energy. When you get your electric bill and you have so many kilowatts that are being kilowatt hours that are being delivered to you, that's equivalent to joules. You're really canceling out the times. Watts are really joules per second. And if you multiply joules per second times time, which could be in seconds, then you're left with joules. So your electric company right now is billing you in the number of joules you use, but they don't call it that. They just call it kilowatt hours. But that's how important joules are. And the energy of an elementary radiator perhaps might be a little bit too abstract for people to accept. But the elementary radiator literally is either a quantum of space or a quantum of matter. And whether you look at either one, you're still looking at zero-point energy fluctuations being present there. And this graphic actually shows the concept of zero-point being on a spring that's moving randomly. So you get basically a random signal and random fluctuations. Now, the interesting thing is that as we look at the fluctuations in general, we may not necessarily conceive of an important way to use that or understand the value of it. And the way I approached it, first of all, as I was looking at a number of different experimental approaches, is I wanted to get a philosophical understanding first. And what I came across was this particular theorem. And it's a systems theory theorem, and the fluctuation dissipation theorem essentially introduces and proves that zero-point energy is intrinsically connected to the concept of dissipation. And to me, this was, counterintuitive. In fact, it's still to this day, I believe, for many of us who've studied this, it challenges you to understand why is there any relationship between the two phenomena at all. So let me explain what this is. When we first start with this particular article, this is from 1951. And in 1951, Callan and Welton basically published a very short article and very readable article called Irreversibility and Generalized Noise. And in the title of this article, you see the essential components of the fluctuation dissipation theorem. In fact, they basically prove it in their article. So in Physical Review, Volume 83, 1951, they were introducing that this concept of generalized noise in any system and an irreversibility of energy loss is actually intrinsically the same thing. There are two sides of a coin, perhaps complementary in some way. And he originally applied it to what's called Johnson noise. Now, the reason I emphasize Johnson noise is that we've now just received a breakthrough, and I'll refer to that in a later slide, where Dr. Beck from London University has shown that Johnson noise now is the best measurement of zero-point energy. And he's comparing it with dark energy, which is the universe's term, astronomer's term, for the universal acceleration of galaxies away from each other. So back in 51, this was already the starting point. You know, goes around, comes around. Well, you're sort of seeing that right here. And electroengineers will recognize the Nyquist concepts. And the basic equation essentially looks at a resistive component and an energy component. And it applies to electrical systems, to various weather systems. You'd be surprised how much diverse applications there are in this article. But the existence of any dissipation, like radiation resistance, necessitates the randomly fluctuating electric field. And the authors actually apply this to the electric field concept, because originally the zero-point field was simply called the all-pervading electromagnetic field. And it was funny, in my work at State University of New York in Buffalo, the only time I heard God ever mentioned in a physics class was when the zero-point electromagnetic field was mentioned. And this was a Chinese professor, as a matter of fact. And I was very intrigued. But it's perhaps because it's so philosophically challenging that this field is all-pervading and so energetic. So to quote from the Callan and Welton article, they state, quote, "Generally speaking, if a system is coupled to a bath that can take energy from the system in an effectively irreversible way, just like your drain in your bath dissipates your water, then the bath must also cause fluctuations. The fluctuations and dissipation go hand in hand. We cannot have one without the other. The coupling of a dipole oscillator to the electromagnetic field has a dissipative component in the form of radiation reaction and a fluctuation component in the form of zero-point vacuum field. Given the existence of radiation reaction, the vacuum field must also exist in order to preserve the canonical commutation rule and all it entails. And so the existence of radiation impedance for the electromagnetic radiation from an oscillating charge is shown to imply the fluctuation electric field. And of course, that yields the Planck radiation law. So to me, this is a fascinating part, because the zero-point field, in many ways, has been allowed to be fluctuating. You don't necessarily allow for energy to come from it, but this particular one phenomena describes that radiation resistance has to be a part of it. And it becomes even more significant when you look at spontaneous radiation. The spontaneous emission from any atom that's sitting there, many of us might know the difference in physics class, for example, even in high school physics, where they teach the basics of lasers and the laser operation. Well, as you look at the laser operation, you're looking at an inverted level, and you stimulate the electrons, and then they fall and give a light out. And it's coherent emission. Well, stimulated emission is one thing, but nature has also had spontaneous emission forever. In fact, everything that you're looking at right now has basically spontaneous emission. In other words, the atoms choose when they want to emit light. And even if they have an input of energy, there's a certain amount of uncertainty for the emission to take place. Well, as it turns out, it's been proven mathematically now that there's half and half sharing. Radiation reaction contributes half of that, and the zero-point field contributes the other half. So, without beating a dead horse, we've now got a very important fundamental understanding that the average concept of zero-point fields basically have this extra radiation reaction that's an integral part of it. And we discover many other phenomenal fields and related interesting applications for it, just from looking at the discoveries that are being made literally day by day. This particular one, as a matter of fact, is showing a practical application that's dealing with motion. And I was fascinated to read, once again, as I warned you, that the standard literature is now catching up to the concepts that we're basically dealing with an emerging technology of energy that no longer can be attributed to being conventional. Dr. Fiegel is the inventor of this concept of applying motion from the zero-point vacuum. And it basically uses the polarization of the vacuum. Whenever you polarize something, you're introducing an electric field. And the electric field basically allows for a particular direction. A strong electric field and strong magnetic field perpendicular, using Lenz's law, for example, Lorentz force rather, would interpret and demand a velocity that's in the third axis, perpendicular to both of them. And that's exactly the way Dr. Fiegel proposes to get motion directly from the zero-point field. And presumably this would apply to charged particles, but he actually says in the literature that it applies to dielectric substances. And once again, we're looking at the free energy concept. This is Nature magazine that I'm quoting from. And in fact, it's a very recent Nature magazine as well. I might as well. Nature, February 2004. And it's called Movement from Nothing. Now the quote is, "The whole idea of getting movement from nothing sounds like a gift to advocates of the perpetual motion machines." Nature magazine, man. But there's nothing in Fiegel's theory that violates the fundamental laws of physics. So this doesn't provide a way to cheat the universe and get free energy. You know, we're a threat to the establishment, I guess. But really what he's saying there isn't true. Because Fiegel is cheating the universe and getting free energy, but he's doing it in a way that's allowable. And that's really what we're all about, is to find ways that you can cheat, maneuver the rules, and as I'll show you, even perpetual motion is now crumbling. 2 out of 3 correlates of the perpetual motion rules are now being violated. And so here we're looking at 50 microns per second. It's actually several centimeters per hour. It really applies to nanotechnology. And what I find is that nanotechnology is a huge field. I've attended one of the industrial meetings at a legal firm that hosts these monthly, and there's lots of entrepreneurs who are just begging to invest in nanotechnology because they're seeing it as the wave of the future. We're going to have nanobots everywhere. You know, go see iRobot if you want to get an image of what macroscopic things could happen. But microscopic things are already happening. And what I find very disturbing is that the nanotechnology field is expanding. There's lots of little motors that work just from molecular machines, and yet they have no way to power them. I attended a AAAS meeting of just 3 years ago, 2001, and the nanotechnology workshop from IBM, the IBM crew was there, they had a press conference as well, and their nanotechnology lab was basically looking for a nanodiode. And that was 3 years ago. So what I find fascinating is that they haven't found their technology, but of course they're still building their motors. And it reminds me of one of the cartoons I saw where supposedly it was on a restaurant table that they were describing a person building a wooden motorcycle, but it didn't have a motor. But he was predicting that he would be able to power it someday, and then he could actually, he invented the motorcycle without a motor, you know. And that's exactly what the IBM and other nanotechnology labs have done. They have motors without the power. But what we're finding is that other physicists are offering the technology that they can marry with nanotech and basically get self-running devices. So Fiegel is the first one to use zero-point energy to satisfy energy conservation. And I salute him for doing that because it's always a manipulation of words. When you deal with something so fundamental that's continually in motion, has a sea of energy, and yet you're somehow saying, oh, we can't use that, you know. So the application of the laws and explaining how zero-point energy can be biased That's what these electric and magnetic fields do, is bias the vacuum so it can only move and oscillate and randomly fluctuate just in one direction. And then he basically biases the blue and red arrows so he gets simply one direction all. In fact, this is the momentum difference for a dielectric material. And we're talking about, for the scientific crowd, the 100 kilovolts per meter, which is not tremendously high, and also 17 Tesla, or about 170 kilogauss. Now, 2004, I'll tell you, this year is probably one of the best years for zero-point energy I've ever seen. Would you believe in Aviation Week and Space Technology, March 1st, 2004, we got a whole article, which of course Hal Puthoff sends me 2 copies of, making sure I know it's getting recognized. That's the only time I hear from Hal Puthoff, when he's got a new publication that says how great he is. But here's the subtitle for Zero-Point Energy Emerges, and maybe the key to deep space travel. Now, I've already shown you one experiment that's proposing a way to induce motion on a subatomic or nanotechnology scale. But now we're describing, can you get hypersonic speeds and miles, per second, and 1,200 seats in your hypersonic flyer. And also, in the meantime, we want to extract energy as we do it. We don't want to just put it on board as a gasoline engine and hope we burn our way to Mars, or to the next star. And that's what NASA's doing now. I went to a NASA meeting, for example, where they're talking about destroying the shuttle, and they have nothing to replace it. And of course, there's all kinds of other depressing things about NASA too. But it's up to a lot of other folks and scientists to say, yes, we do have prototypes, we have discoveries, we can engineer this stuff, and now's the time for government grants to get together. And luckily, Dr. Mile is a good example, who's already been acknowledged by the Department of Energy, and he'll be giving a seminar, I believe, is it this coming month? Oh, okay. But I was understanding that at least the government here in the United States is perhaps arranging a seminar from you. And I see. Great. Well, we'll look forward to that. Because they need to be educated. Our government's in the 20th century, which is old technology. So here I'm proposing, and this is a very conceptual issue. We have 2 problems here that this article proposes. Not only motion, but I want energy too. And that's why our nonprofit institute is devoted to energy and propulsion. Because in every experiment, you'll find that they're both related. And if you get one, you might as well get the other, because you're going to need them. And you can't imagine traveling in space without both. Onboard, convertible, as you need it, without heavy weights of who knows what. I saw a science program just this last week where this guy was proposing an inflatable inner tube that he's going to put moon ice in to be able to burn a steam engine on his way to Mars. I thought it was the best invention ever, whatever. So, but good luck to him. So, now we get to the more practical physics of zero-point energy. How do we really get powerful motion that applies fluid dynamics to things that your school teachers never taught you? My stepson says that his physics professors elucidate the physics that he learns. And I said, did they tell you about quantum entanglement or quantum teleportation? No. So the elucidation process is definitely needed here. Hydrodynamic model of vehicle interactions with a zero-point field. Now that's a mouthful, but hydrodynamic is basically fluid dynamics. Let's look at sound. If we look at subsonic sound, subsonic flight, for years, the speed of sound basically was a barrier. It was treated as a barrier. Nobody ever thought you could break the barrier. Even Chuck Yeager was worried when he got into his flight path to break the sound barrier. But the strange thing is, if you look at the drag and you plot it as a ratio of velocity over your speed limit, which c here represents the speed of sound, you get a nice curve whose equation matches exactly what we're faced right now exactly the same equation for superluminal or subluminal flight. Right now we're in the subluminal flight mode. Every textbook on relativity tells you, this is what you memorize, this is your speed limit, and you can't go faster than the speed of light. Nothing can go faster than the speed of light. And of course then there's another equation which describes the drag constant. And you get the same type of buildup in the fluid medium that you do for sound. And this to me also was very fascinating because this equation here, if you can't read it too well, is also reproduced over here. And once again, we're looking at permeability and permittivity. Now, as we look back on the previous slide, which I might as well, since I've got lots of time here, is to go back a few slides here. Whoops. Maybe I won't go back. Okay, good. I'm stuck with a little arrow here that I'm not sure what it means. Well, I tried to go back and I shouldn't have. Help. Just if you can remove that little gray box there because I'm actually pointing to it. Oh, I got
This toggles it from a mouse
Okay.
to a page up, page down.
Okay.
Or page advance, page read. You know, now you got
Okay.
it. You can,
I'll stay where I am. This is good enough. But previously we did mention that the temperature dependence and impedance was directly related to permittivity and permeability. And now we're seeing it once again pop up as a very important parameter. Now the Lorentz force compared to the zero-point field, this is actually an outgrowth of Puthoff's work. Puthoff's work is now being applied to this particular experiment. And Einstein-Hopf drag is exactly the analog in the light mode, as you see with the aerodynamic drag in the sound mode. And so what is exciting to me is that when you talk to people at the DOE, for example, Dave Hamilton, who runs an electromagnetic talking group, a very interesting scientific exchange group, which is mostly internet-based, you find them talking a lot, even as the Bearden group does as well, on non-abelian electromagnetic fields. And essentially that mouthful basically describes a non-commutating field. In other words, if you multiply A times B, it's not equal to B times A. And if you allow that non-commutation to apply, you get a whole new physics. And that little change means that order is important as you apply fields and as they're multiplied. And also, of course, the other important thing here is the toroid. Fronig's work basically was at the Joint Propulsion Conference just a couple of years ago, 2002. And that number is 3925. So this paper is actually available from AIAA, and there's a library also that gives you hard copies or soft copies. And there's also some description of it too, but let me just skip ahead to the next slide and show you a picture of how it works. Oops. There we go, one more. Here's the Fronig's concept of the superluminal saucer. And let's see if I can point out a nice, interesting quote that he points out too. The non-abelian analog basically allows for the forces, essentially the resistance representation R can be changed by surrounding the saucer-shaped starship with a toroidal electromagnetic field that distorts and perturbs the vacuum sufficiently to affect its permeability and permittivity. The vacuum perturbations are simulated by fluid field perturbations that result in the percentage change of the disturbance that basically allows for a big improvement and a reduction in the drag. And this is probably the most important part. In other words, so far, whenever we've considered moving through a vacuum or moving through a medium, you're always concerned with how the medium interacts with the vehicle. So far, as I explained before, the vacuum is treated as an empty vessel. So we never think of the vacuum as resistance. But inertia proves that we do have resistance, and even gravitational forces also show that. So what Fronig did here was to apply the fluid dynamics laws and perturb the vacuum with a toroidal electromagnetic field. And for those of you who are not familiar, a toroid simply is taking like a solenoid, a coil of wire, and winding it together to form a donut. So as you form the donut, the magnetic field's inside internally, and the A field, if the donut's, say, in my hand, the A field, the vector potential, is vertical. And it's a very unique field. There's lots of properties of the vector potential. And here's another good example. And if we allow for the temperature to basically approach absolute zero, wouldn't you know the nice coincidence is that the outer space temperature is around 3 degrees, absolute zero. So we have a very convenient enhancement of this phenomena by going out into space, which we cannot get when we're close to Earth. And of course, you get this accelerating recoil. And the other special bonus is it transfers energy from the ZP field as well. And that's perhaps the most surprising conclusion, is that you not only get this motional effect of force, unidirectional force, which he's trying to show here. This is actually a 1 over, it's a minus, so we're seeing a reduction on both sides. And so the vehicle is being pushed in one direction based on the negative perturbation of the vacuum field. So far this is in the conceptual mode, but the nice thing is the physics has provoked enough people to consider putting it in the experimental mode. Now another experiment that is perhaps nothing can get physicists more irritated and upset than basically say that we can get energy from a single heat bath and we don't need a temperature difference. Because what they basically think is that you're violating the second law of thermodynamics. Well, as a matter of fact, they are violating the second law of thermodynamics. And it's been in Science magazine in 2003, just last year. And it's also providing a lot of controversy. And of course, this is a big pillar of defense that's being collapsed now. And it caused a lot of exchange of letters and responses to the editor as well. And in fact, let me read the little description. And this is from a similar author who actually predated Scully's work, and he describes even more of the violation details. For example, the Casimir, the analysis of the Casimir engine cycle demonstrated a departure from the hydroelectric gaseous, that's in our next approach. This is our photo Brownian photon and Carnot engine. And what the Alavirden points out, and I'm happy to say this was brought to my attention from the Binotech conference a couple of years ago in Germany, whose some representatives are here today. And what Alavirden points out is that our main results are rather dramatic, apparently contradicting the second law. We show that the Clausius inequality, which is dq being always less than temperature times the difference in entropy, can be violated. And that it is even possible to extract work from the bath by cyclic variations of the parameter. And they even throw in, parenthetically, a perpetual motion device. And the physical cause for this appalling behavior will be traced back to quantum coherence in the presence of a near equilibrium bath. And it's emphasized that quantum coherence is reflected in the quantum noise correlation and so forth, more technical details. But the most important part is that we're literally describing something that's very similar to a micro laser cavity. That's literally what we're looking at here, is a micro laser cavity. And all we're proposing is this unusual phrase called quantum coherence. Well, that simply is a phase difference. And if you allow for a phase difference, you can then have a temperature difference internally that basically rotates or circulates radiation. And so radiation essentially is the medium to drive the piston. Radiation pressure is what drives this piston. So once again, this is a theoretical model. However, it is so provocative that it's also provoking other experiments. And as we look at the micro laser, here's an artist rendition of what a micro laser would look like. 2/millionths of a meter across and about 100 nanometers thick. And these microlasers basically achieve the lasing without an inversion. And this is a major breakthrough because quantum mechanics is being applied here in a new application that essentially doesn't seem to make sense in terms of people who are used to the old style of lasers that required inversion. Now here's another one that uses a microlaser, and once again, this particular article, which was in Physical Review B, 1999, it's Dr. Pinto's article, mentions free energy in the abstract. He says if this thing works, it'll basically provide unbounded free energy. And I was very pleased to see his courage at getting Physical Review even to include that and not edit it out. Now this cavity tends to be a little bit complicated. I would criticize Pinto because of the complex nature of this cavity. We're seeing something very similar to forward, where you have a membrane or a plate that's being moved by charge and the Casimir force. In other words, there's a movable plate, Casimir force here, charge upwards, and we're applying a little bit of voltage as well. Now the trick here is, and this is a zero-point energy trick, you discover these in the literature, and of course Pinto is now using one of them. The trick is that as you turn on your micro laser, you change the dielectric properties of the surface and instantly increase the Casimir force. Just turn a light on and you get a bigger force. Hello, free energy? Pinto probably couldn't sleep for a few days after he discovered that. And just changing the dielectric properties, all of a sudden the Casimir force gets bigger and pushes this thing upwards just because this little light went on. So this is literally the entire secret to his whole, I think it's a 15-page article, is that altering the physical parameters therefore changes the total work done, and it's unique to the quantum world. You can't do this in the macroscopic world. You have to do it on the microscopic, nano size invention. And of course, this also involves the radiation of virtual particles. And of course, even as you do the thermodynamic closed paths, the total force does not vanish. So you are getting energy out. Now, how much energy out? Right now, he's estimating 1/2 of a nanowatt, 10 microjoules per centimeter squared. If you look at the surface area here, this is 50 to 100 microns. And so it's still on a microscopic scale. This is not a nanotechnology device. This is really a micro technology device. And the application, perhaps most important, is not only the frequency of kilohertz, but also the hope that you can multiply these to have them all working significantly in series or in parallel. And so Pinto literally today is building these and hoping to see a breakthrough. Now, along the same lines of moving something, the very fascinating, I would say, family of technologies that's also available today is the fluctuation-driven electricity. And as we look at the reasons for it, there's, first of all, the fluctuation theorem that has basically described experimental proof that as you perform experiments on something where you deliver heat to a system, half the time heat is also delivered back to the source. It's a probabilistic type of system. And this was in Physics Today, actually, the article describing the fluctuation theorem. And so I found this very fascinating. In fact, here's the article, Crookes Physical Review E, 1999. So the negative work concept is free energy. When you're not working, you're basically relaxing, and somebody else is giving you the work. And this is essentially what they're describing here. So there's a number of examples. This is one system which Linke in Science in '99 has proposed, that if you design a ratcheting system, which they experimentally did, this is a ratcheted semiconductor layer of pockets to allow for a particle to keep moving along the road if you apply a fluctuating potential. And once again, you see this up here as well. As you apply a fluctuating potential, you get a net current. So overall, the input force can be zero, but you also do get motion. And so on the nanotechnology arena, we're seeing the quantum ratchets being a buzzword. That you can also now prove that thermal noise can be rectified. And to me, this is the most exciting, simple, clear-cut direction that all zero-point energy nanotechnology research should actually pursue. And associated with this in Linky is also the fact that as we look at the type of devices he's working with, there's about 0.2 nanoamps or a picowatt that he also develops. And I promised I would review basically the perpetual motion concepts. It obviously exists in electron motion consistently. In fact, there's now research that Puthoff has published showing that every single electron level is being bolstered by the zero-point field. And right now, we basically already have perpetual motion devices of the second kind, where, for example, in laboratories for over 10 years, a superconducting current has circulated with no need to add extra energy. And this has also baffled the industry because they always thought they'd have to get rechargers for the NMR units, the MRI it's now called, for units. So this is completely converting energy from one source to another, and we're thinking that that would be the violation. Actually, this is the third kind, I'm sorry, where it continually moves forward in one direction. And what we're finding is the second law is now being eroded by a couple of the inventions I showed you, especially when you're dealing with the steam temperature. And the conservation of energy, which basically is the perpetual motion law of the first kind, is being violated, but you have to account for the zero-point field as a source of energy. And so in 1998, the big buzzword was the universe is accelerating, and Einstein was right. The cosmological constant should have been included in the general relativity equations. And yet he took it out. So originally in this article, they actually talked about zero-point energy being the source of the problem, why the galaxies were expanding. However, as time went by, the astronomers decided to change their language and call it dark energy. And I've been at more than one conference where I keep asking them, why are you calling it dark energy? There's no such thing. You know, it's zero-point energy. And they said, well, we wanted to keep it vague. You know. Let's confuse the issue. That's scientific method, all right? Yeah. So in a wonderful, courageous attempt to bring this diversity or divestiture back into the fold of physics, we just have July 8th, 2004, Nature magazine reporting on Dr. Beck from London University. And this is the only source right now of this article. But this reference actually is repeated, and it will be in my future Energy e-news as well. If you're interested in getting on the email list, just let us know. And what this gentleman has done, the scientist has pointed out, is as you recall the previous equation I showed you from Planck's second law, the interesting thing is that without the zero-point energy term, you basically would have the dotted line approach. But with the zero-point field, you'd have all of these paths for the spectral density. And the interesting thing is the spectral density in Josephson junctions, which is basically a noise-driven system, which allows for tunneling in superconductors, turns out to follow the graph that includes zero-point energy. And what he found very fascinating, besides this particular graph, notice the frequency goes up to around 10 to the 12th, is that they also map over to the dark energy spectrum. Now, he would like to propose that the cutoff for zero-point and dark energy are the same, but there's a lot of controversy for that, and I won't even get into that issue, because the cutoff for zero-point may be much further for many reasons. But the fascinating part is we can now look at Josephson junctions or diodes as being a source of zero-point energy. And he's, of course, saying dark energy equals zero-point energy. So what do you do with a number of different fluctuating systems if you know that the thermal energy really is no use, or the non-thermal energy is really no use if it goes in both directions? Well, electrical engineers like us basically want to use a diode and force it to go in one direction only. And so a thermoelectric noise, it's called. You find quantum noise, non-thermal noise, but basically in any circuit, when you get to the lowest level possible, you get a mixture of both, especially if you're at any temperature above absolute zero. And these three patents I would recommend is perhaps the most significant discoveries that have been patented in this field. For example, metal-to-metal diodes, if you study this Brown patent, 3890161, that'll give you a really good estimation of the engineering approach to applying sheets of metal-to-metal diodes, which basically have very low forward drop and the potential for the application. The Yater patent I'm not that excited about because he has to use a battery to get the thing working. So even though I analyze it in my feasibility study, I'm not recommending it. However, the Capasso patent, which is an AT&T patent, 4704622, is a very solid zero-point energy tunneling diode patent. And what's fascinating about Capasso is he actually acknowledges zero-point tunneling is the only source of activity for that diode. This, to me, was the best patent you could ask for to verify the fact that ZPE is real. Here's a physical device that doesn't work if zero-point energy doesn't exist. And so even though Yater's, as you can see here, this is a Yater diagram with the voltages being applied, there's the best example is perhaps a diode sitting by itself, unenergized except by the zero-point field. And so just recently now, in 2004, Yasutomi in Science Magazine has pointed out there's a number of molecular diodes that are also available. Now these particular ones that we see here are peptide molecular photodiodes, about 1 nanometer. And of course, this would be the ideal to work with a single molecule. But in this particular instance, they also require organic end pieces that are receptors for photo input. So these would not be recommended, but it does give you the appreciation for the fact that molecular diodes are now becoming available. And I feel very excited about that. Let me go a few more minutes beyond this, just so I can then get into the Q&A if I could.
How much you need to wrap it?
About 10, yeah.
Go for it.
Oops. Oh, here we go again. I'm trying to back up. Yeah. Hey. Okay, so to conclude here, we basically are looking at...
Push that button again. So
yeah, thank you.
now it goes back to up and down.
We basically are looking at a number of... Whoops, I'm at... We'll get it straight here. Okay. To summarize the findings and the technologies that are reviewed, at the top, we are looking at, for the Mead patent, for example, I examined microspheres, nanospheres, picospheres, and femtos. And it's fascinating to find physical representations of each of those in nature. For example, on the, I believe it was the nanosphere range, you basically find there's a leukocyte that, or I think it's a micro. Yeah, it's on a micron scale. A leukocyte that basically is fighting Casimir forces to maintain its spherical size. And we find many examples of that now that biophysics and quantum physics are being really related. And you can use the E equals mc squared to get an appreciation of the energy that's available in a mass that size. And when you do the calculations, I just had a discussion about this earlier today, that the energy density tends to increase as the size gets smaller. This is a very controversial statement, and we can only state that the physics and the equations predict that, but I can't really defend it because it's counterintuitive. It doesn't make sense. Why would we have a milli EVs in this realm, and then we got mega EVs in the femto region? But that's what Mead points out, that his collectors got smaller. He basically had a more powerful system, and zero-point energy constantly predicts that. So we'll leave that, as many parts of zero-point theory has been done. We leave it on the shelf until somebody proves it to us. So after you look at the technologies, what I did is put them in table form and apply the feasibility to each one. The feasibility of the electromagnetic spheres, where you focus, I didn't even tell you about focusing. You can actually focus zero-point energy to a particular area. Just like a parabolic dish does, you can do the same with ZPE, which is also gets you thinking, a lot of ideas of increasing effects. These are moderately feasible. I would even see poor. I apply a poor feasibility to these, just because of a number of extenuating circumstances that are involved. The mechanical approaches, which we talked about a few of them, for example, Pinto's approach and several others that involve mechanical systems that move and try to use the Casimir force. There are several, in fact, more than a half a dozen mechanisms where you can get Casimir forces to repel or Casimir forces to attract by changing the magnetic field, the temperature, the permeability, and the impedance, as we pointed out, and the dielectric constant by illumination. So all of those try to apply it, including spatial squeezing and so forth. But together, all of those are moderate feasibility. The highest rating, or I would say high rating, would be applied to the fluid dynamic approach for many reasons, but there are 3 different ones that apply fluid dynamics. And this to me is very exciting because all of a sudden we see an approach of motion. And receiving motion from the zero-point field is certainly everyone's dream, to get to the stars, of course. However, if we want to start today and get engineering nanobots to really run around like the sci-fi movies show us, the highest feasibility are basically for the thermodynamic approaches, including Goychuk. Goychuk I didn't give you the reference for, but it's in my study. It's Physical Review Letters, Volume 81, 1998. And he essentially describes quantum Brownian rectifiers. And he does so in such precise terms, in terms of the predicted curves and demonstrations, that whereas before we talked about having a voltage necessary, you don't even need that. He proves that all you need is the quantum stochastic dissipation. And so that's the summary. And the recommendations are that we should be pursuing metal-to-metal nanodiodes, and they probably hold the key to using simple transducers that can achieve watts per square meter for delivery. Many technologies, a couple I pointed to, show you how to apply these in 2-dimensional sheets. And of course, then you can stack the sheets. And they're temperature independent, which is a fascinating part. And they work 24 hours a day as well. That's another very important part of all of this. Ratchet-like asymmetries, as we saw, were more related to the thermodynamic approach. But as Goychuk points out, if you get the tight binding crystal lattices, that is perhaps the secret to applying stochastic resonance and achieving rectification. In other words, you get current flow just by applying the correct quantum mechanics on a randomized approach. And the other word for applying it to the photocarno engine is quantum coherence, where you just look for a phase difference. And that certainly is interesting as well. And the last one is the electromagnetic field effects, which are encouraging for propulsion and transport. So, thank you very much. And if you have any questions, feel free.